25.7. An atomic description of dielectrics. This lecture will cover the microscopic view of dielectrics, focusing on several key topics. We will explore the polarization of both polar and nonpolar molecules when placed in an electric field. We will also examine how this polarization leads to an induced charge density and alters the internal electric fields within the material. Furthermore, we will analyze the effects of inserting metallic slabs into capacitors and calculate the resulting equivalent capacitance. Finally, we will determine the capacitance of capacitors that are only partially filled with a dielectric material. Let us begin with a microscopic view of dielectrics. When a dielectric is introduced into a capacitor, it reduces the potential difference across the plates by a factor called the dielectric constant, denoted by the Greek letter kappa. This reduction in potential difference occurs because the internal electric field decreases. Specifically, the new electric field equals the original electric field divided by kappa. To understand why this happens, consider a dielectric made of polar molecules. Without an external electric field, these molecules, which act as tiny dipoles, are randomly oriented. However, when we apply an external electric field, it exerts a torque on these dipoles. This torque causes the molecules to partially align with the field, a process known as polarization. Let us visualize these polarization mechanisms. Initially, polar molecules are randomly oriented in the absence of an external electric field. Listen. When an external electric field is applied, these molecules partially align themselves with the field. The degree of alignment increases at lower temperatures and with higher applied electric fields. Even for nonpolar molecules, the external field induces a dipole moment, leading to an induced polarization that also aligns with the field. As a result of this alignment, the charged edges of the dielectric act like an additional pair of parallel plates. This forms an induced electric field directed opposite to the external electric field. When a dielectric slab is placed between charged capacitor plates, it develops an induced surface charge. Specifically, an induced positive surface charge density appears on one face, and an equal magnitude negative surface charge density appears on the opposite face. These induced surface charges create their own induced electric field, which points in the opposite direction to the external electric field created by the capacitor plates. Because these fields oppose each other, the magnitude of the net electric field inside the dielectric is simply the external field minus the induced field. We can express both fields in terms of charge densities. The external field is the plate charge density over the permittivity of free space, and the induced field is the induced charge density over the permittivity of free space. We can calculate the induced charge density by using the relationship that the net field equals the original field divided by kappa. Substituting this into our previous field equation, we find that the plate charge density over the product of kappa and the permittivity of free space equals the plate charge density over the permittivity minus the induced charge density over the permittivity. Solving this for the induced charge density yields an expression. It equals the plate charge density multiplied by the quantity kappa minus 1, all divided by kappa. Because kappa is always greater than 1, the induced charge density is always less than the charge density on the capacitor plates. Interestingly, if the material is a perfect conductor, the internal electric field is 0, which implies kappa approaches infinity. In this limit, the induced charge density perfectly equals the plate charge density. Let us look at an example involving the insertion of an uncharged metallic slab of thickness A into a capacitor with a plate separation distance d. Because the slab is a metal, the electric field inside it must be 0. Any charge on the capacitor plates induces an equal and opposite charge on the nearest face of the metallic slab. The metal between these induced surface charges just acts as an electrical connection. Therefore, we can model this single partially filled capacitor as two empty capacitors connected in series. Each of these equivalent capacitors has a plate separation distance equal to d minus a, all divided by 2. To find the total capacitance, we use the formula for two capacitors in series. The reciprocal of the total capacitance equals the sum of the reciprocals of the individual capacitances. Substituting the expression for each capacitor, we add the reciprocal of the first capacitance to the reciprocal of the second. Simplifying this sum shows that the resulting equivalent capacitance is the permittivity of free space times the area, divided by the quantity D minus A. Notice that if the slab is infinitesimally thin, meaning A approaches 0, the capacitance returns to its original value for an empty capacitor. Furthermore, this final capacitance only depends on the thickness of the slab, meaning it is entirely independent of the slab's vertical position between the plates. Now consider another example where a dielectric slab, rather than a metal slab, is partially inserted into a capacitor. The original capacitor has A plate separation D. The dielectric slab has a thickness equal to A fraction F times D, and it has a dielectric constant kappa. We can imagine an infinitesimally thin metallic sheet at the bottom of the dielectric, allowing us to model this system as two capacitors in series. The first equivalent capacitor contains the dielectric, has a separation distance of F times D, and its capacitance includes the factor kappa. The second equivalent capacitor is filled with air, has a separation distance of 1 minus F, all multiplied by D, and acts as a standard empty capacitor. To solve for the total capacitance, we again apply the series combination formula. We add the reciprocals of the two individual capacitances. After finding a common denominator and simplifying the algebra, we can express the final capacitance in terms of the original empty capacitance. The final capacitance equals kappa divided by the quantity F plus kappa times 1 minus F, all multiplied by the original capacitance. We can check this result by looking at its limits. If the fraction F approaches 0, the dielectric disappears, and the capacitance returns to the original value. Conversely, if F approaches 1, the dielectric fills the entire space, and the capacitance becomes kappa times the original capacitance, as expected. In summary, introducing a dielectric into a capacitor decreases the internal electric field by a factor of kappa. This reduction is caused by the alignment of polarized molecules, which generates an induced electric field that opposes the external field. Consequently, an induced charge density appears on the surface of the dielectric. This induced charge density is always less than or equal to the charge density on the main capacitor plates. Finally, we learned that inserting either metallic or dielectric slabs that only partially fill the space between the plates can be effectively modeled as series combinations of multiple smaller capacitors. To conclude, please consider these review questions to test your understanding. First, why does the induced surface charge density on a dielectric never exceed the charge density on the capacitor plates? Second, when a dielectric slab is only partially inserted into a capacitor, explain why we can model this system as two capacitors in series. What is the physical justification for inserting an imaginary thin metallic sheet between the layers to help us with this model? Thinking through these questions will help solidify the concepts of polarization and capacitance discussed today.